Hi, so this is our revision video for topic 3, which is waves. It will be in 2 parts. Okay, well, first of all, you need to know what a wave is. If you remember, we had a discussion about this. You need to be able to write this down. So waves can transfer energy and information, that is sometimes called a signal, but without transferring matter. Okay, so remember, the energy moves, the information moves, but the material that's transmitting the wave stays where it is. And they involve vibrations of some sort. Oscillations is just another word for vibrations. You can use either of those words. Okay, there are 2 main types of waves. Transverse waves. The oscillations are perpendicular to the direction of energy transfer. You can see the label here. We've got the top is called the peak, the bottom, in English you pronounce this word trough. So peak and trough. So if we look at that a little bit clearly, you can see very clearly that the waves are moving in from left to right in the page. But if you look at any particle, you'll notice that it's vibrating, in this case, up and down. Yeah, so this one's vibrating up and down. Let's pick one here. This one's vibrating up and down. In fact, the vibration is identical. It's just at different times. We'll talk a little bit more about this in year 12. This is something called simple harmonic motion. But you can see the vibration is up and down. The waves are going this way at perpendicular. That's at 90 degrees. Okay, so this is an example, yeah. So the wave is going from right to left. Yeah, the people are oscillating up and down. The soldiers here, yeah, the wave is going this way. The soldiers are going up and down. So this is an example of a transverse wave. The oscillation is at 90 degrees to the direction of energy transfer. Okay, so small water waves are transverse waves. The big water waves get a little bit more complicated. Light, we'll talk about later, is a transverse wave. We can make a transverse wave on a rope or a slinky spring. And there's a type of earthquake wave called an S wave, which is a transverse wave. The other type of wave are longitudinal waves. This time the oscillation is parallel to the direction of energy transfer. Now, instead of peaks and troughs, we now have compressions and rare refractions. So let's have a look at that in a bit more detail. So you can see these waves are travelling again from left to right. But again, if you look at any particle, let's look at this particle here, it's vibrating to left to right as well. Okay, pick any particle at random, it's vibrating exactly the same way, just at different times. So the vibration is left to right, the waves are traveling left to right, the vibration is parallel to the direction of energy transfer. Okay, so sound is a longitudinal wave. We can make longitudinal waves on a slinky spring. And there's another type of earthquake wave called P waves, sometimes called pressure waves, and they are longitudinal waves. Okay, well, when we're measuring a wave, we can measure its amplitude, the maximum displacement from the mean position. If you think about it, even a longitudinal wave, it will go backwards and forwards around an average position. Notice this is measured from the average position to the top. It's not the full height of the wave. We can measure the frequency, so the number of waves that go past a second, or the number of oscillations per second. This is measured in hertz. So 50 hertz is 50 vibrations or 50 waves in 1 second. We can measure the period. This is the time it takes from one wave to another. Okay, so that is measured in seconds. And there is a connection between these two, okay, between frequency and period. We use the symbol big T or capital T for period, that the frequency is equal to 1 divided by the period, or the period is equal to 1 divided by the frequency. In mathematics, we call these reciprocals of each other. We can measure the wavelength. This is normally given the symbol lambda in equations. This is a Greek letter. It's the length of one complete wave. And obviously, we can measure the speed at which the energy is transferred. There is a formula that connects some of those measurements. This is called the wave equation. The speed of a wave is equal to the frequency multiplied by the wavelength. And this is true for any wave. But be careful to use the right units. Okay, so meters per second, meters and hertz. And of course, we can write that as a triangle if we need to arrange it. So frequency is going to be speed divided by wavelength. Wavelength is going to be speed divided by frequency. And of course, speed is frequency multiplied by wavelength. Okay, we did some experiments looking at the law of reflection, and you just need to remember that when a wave is reflected, the angle of incidence is equal to the angle of reflection. Notice both of these angles are measured with the normal, very important. We looked at refraction, so we shone a ray of light along the normal, so at 90 degrees to a block of glass, and we noticed it went straight through. However, when we shine a beam of light at an angle, when it enters the glass, it bends towards the normal. When it leaves the glass, it bends away from the normal. So we've obviously, remember, the normal is just an imaginary line at 90 degrees to the surface. So we've got two normals here. You need to remember this. Okay, why does this happen? It's because the waves slow down. You can see here the waves coming in. These could be water waves or whatever. Okay, this side of the wave slows down first before this side, so it has the effect of bending the wave. So light slows down when it goes from air into glass or water, which causes it to bend. Okay, it changes speed. The waves get closer together. Okay, but the frequency, the number of waves per second, stays the same. Okay, we investigated this. Okay, so we shone light into a glass block, we measured the angle of incidence, we measured the angle of refraction, and we found that there is a mathematical relationship between them. That the sine of the angle of incidence, that's the angle here, divided by the sine of angle of refraction, is actually equal to the ratio of the speeds, and we call that ratio the refractive index. Okay, so for glass, this is about 1.5. Okay, the sine of the angle of incidence, the sine of angle of refraction. Now, we did do a worksheet that we used this, and we found it quite difficult. I might do a separate video talking about how to use sines and cosines, because we didn't seem to be very comfortable doing that. So like I said, we did some questions. Okay, just to finish this revision, the first part of waves revision, just going to talk a little bit about the electromagnetic spectrum. This is a Scottish physicist. So after Newton and Einstein, probably the third most famous or important physicist, James Clerk Maxwell. He was a mathematical physicist, lived, as you can see, about 150 years ago. Okay, now he took the formulas that there's been Michael Faraday, so I was trying to think of the name. Michael Faraday had discovered for electricity and magnetism, and he realised that electric fields and magnetic fields can make a wave. So an oscillating electric field produces a changing magnetic field at right angles to it, and a changing magnetic field produces a changing electric field at right angles. So you can actually make a wave. And when he calculated how fast this wave should go, it was actually the speed of light. So he'd realised that he'd discovered what light is. It's an electromagnetic wave. Now, the reason the difference between red light and violet light that we perceive is to do with the wavelength. So red light has a wavelength of about 700 nanometers. A nanometer is a billionth of a meter, so very small. Violet light has 420 nanometers. It's a shorter wavelength. So our eyes, our brain perceives that as different colours. However, Maxwell realised that there was no limit to how small the wavelength could be, how big it was. So scientists then started to look for other types of electromagnetic waves with shorter wavelength and longer wavelength. One of them is ultraviolet waves. So ultraviolet waves have got waves that are smaller than violet light. The wavelength is smaller. Our eyes have not evolved to see this. I think bees can see ultraviolet light. And ultraviolet light is used in sunbeds, as you can see here. It's also used in detecting forgeries and that. There are some electromagnetic waves smaller than violet light, ultraviolet light. They are X-rays. So X-rays are actually light waves. Now they do all the things that light does. It travels at the speed of light, it can be reflected, it can be refracted, and they have other properties as well, of course. So X-rays pass quite easily through most matter, which is why we can use them for medical imaging and things. And there are waves, we're going to talk about these next year when we do radioactivity, because they come from the centre of atoms, called gamma waves, which are also electromagnetic. Now we can go the other way. There are waves that are bigger than red light. We call them infrared light. These are invisible to us. Some animals have evolved to see them, so animals that hunt at night time. And we perceive infrared light as heat. So we have sensors on our skin that can detect it, and we perceive it as heat. There are light waves bigger than infrared. We call them microwaves. Okay, so microwaves are light waves. Microwaves are not only used for cooking, but we use them for Wi-Fi, we use them for cell phone signals, so very useful. And the longest electromagnetic waves are radio waves. Okay, so what do you need to know? Well, you need to know this order. So radio, microwaves, infrared, red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-rays, gamma rays. You need to know that these are the long waves at this end, these are the short waves. And of course, if it has a short wavelength, it must have a high frequency. Yeah, because the frequency times the wavelength will give the speed. So you need to know this order. You need to know that these are short waves, these are long waves, these are low frequency, these are high frequency. You also need to know that they can travel in a vacuum. You need to know the speed. This is a number you need to learn. 3 times 10 to the 8 meters per second. That's 3 followed by 8 zeros meters per second. They're transverse waves. And of course, they're electromagnetic waves. They're made from oscillating electromagnetic waves. Okay, just to finish this, you need to know some things about them. So microwaves, used for cell phones, used for satellite communication, used for Wi-Fi. Obviously cooking in the kitchen as well. Infrared waves, so your remote control uses infrared. They're also used for intruder alarms, so they detect the heat given off by bodies. X-rays obviously used for medicine and for security. Don't put for X-rays. Yeah, X-rays are used for X-rays. Yeah, we need to be more specific about that. Obviously, some of these waves are dangerous. So microwaves can be dangerous at very high power. The microwaves that Wi-Fi uses on your phone are not dangerous, they're very low power, but the microwave that you use in the kitchen could be dangerous. And X-rays as well, of course, can be dangerous, so you're limited to the number of X-rays you have every year if you go to the doctor, because there's a small chance they can cause cancer. Same thing with gamma rays. Okay, you need to know the speed of light, we've already said that. Okay, so we'll finish there, okay, and there'll be a part 2 to this revision video.